Swayam Prabha. Digital India. Educated India.
So far what we have seen is that crystals have many defects, point defects, line defects and two-dimensional defects. So now these defects like point defects, line defects like dislocations for example, point defects like interstitials, they interact with each other and therefore they come in the way of movement of line defects which are called as dislocations. So each of these defects has a role in either making permanent change in shape easier or more difficult. Now here is an example of two-dimensional defect which is grain boundary. We have considered that earlier in the context of high angle grain boundary and low angle grain boundary. We have seen that a low angle grain boundary has got smaller mismatch between two neighboring grains, whereas high angle grain boundary is due to a significant mismatch between the lattice orientations of the neighboring grains. Now these grain boundaries therefore act as regions of high energy because you have a number of defects which are concentrated here. The atoms are not located at their minimum energy positions, and that is because the grain boundary is a highly disordered area, whereas grain has got an ordered structure of atoms or ordered layout of atoms. Yes, there are defects which disrupt this orderly arrangement. So point defects mean that the atom is missing from that particular location, or an interstitial means that another atom which is present not in the regular lattice position but in somewhere in between and in an intermediate position. So there are point defects like vacancies and interstitials, and we have also seen that there are line defects like dislocations, and these dislocations tend to move, and these dislocations move at a stress that is 1,000th of the ideal stress that would have otherwise been required to deform a crystal, a healthy crystal, that is a defect free crystal. But then defect free crystal is a hypothetical concept, and therefore all real world crystals have all the three defects present in them. Well, we do have single crystals of variety of elements. For example, we use silicon single crystal for electronic equipment, manufacture of chips and so on. Similarly, one uses Inconel single crystals for making turbine blades. So there are many occasions or many applications in which you need single crystals to be used, and therefore there is one single crystal, a single orderly arrangement of atoms that is present there. But then again it is not devoid of any of these defects. So the grain boundary is essentially the boundary of the crystal when it is a single crystal, and inside you can have point defects as well as the line defects. So none of the crystals are free from these defects. Now as these dislocations move, basically you have a slip plane here along which the shearing takes place, so the dislocation moves. Once the dislocation starts moving, you say that the plastic deformation of permanent change in shape has taken place, because once you remove the load, the dislocation does not return to its original position. So the plastic deformation is in that sense a permanent deformation. That is because of permanent movement of the dislocation. The dislocation moves from one position to other, and it remains permanently there unless it is moved to a new location. So supposing you take a cylinder of a certain diameter and height h, let us say, and you compress it to h by 2, again pull it back to h, the strain does not become 0, because what you have done is you have moved the dislocations in the material. Dislocations have multiplied inside the material. We have seen the mechanism of multiplication of dislocations. Then while pulling it back from h by 2 to h, you have again added more dislocations. Therefore, the dislocation density has gone up significantly during these two processes. So initial process was to compress, the change in shape was permanent, then you extended the cylinder back to its original height h, again the deformation is permanent. So this permanent deformation is the result of a permanent event called dislocation movement. The dislocations do not come back to their original positions because you have pulled the material back to its original height h. So basically what it means is that permanent deformation continues to add dislocation to the crystal. Now when there are large number of dislocations, when dislocations multiply, what happens is they impede each other's movement, because I gave you an example of moving through a crowd. So as the number of people increase, your free movement gets impeded. You meet people coming in the way, and therefore your movement is not as fast or is not as free as it would have been if the road were empty. So the dislocations therefore get held up at for various reasons. Either they impede each other's movement, or their movement is impeded by the interstitial. So now interstitial is a point defect, it interacts with the line defect, namely a dislocation. So this way these point defects interact with the line defects, impeding the movement of the line defects. Now these line defects continue to move depending on how their movement gets impeded. So if the movement gets impeded, you need a higher force. I mean, if you want to continue the plastic deformation or permanent deformation, then you need a much higher force, so that the high force results in further movement of dislocation. But then as the dislocation moves, it gets further impeded by the neighboring dislocations or dislocations which generate as a result of multiplication of the dislocations, or interstitials which are present, which are deliberately added for alloying. For example, in case of iron, carbon atoms are added, and that makes it steel, and then the strength of the steel comes from these interstitial carbon atoms impeding the movement of dislocations. Now the strength of the resistance to deformation of the material increases as the impedance to dislocation movement increases. Now let us say that the dislocation continues to move and then comes to this region called as a grain boundary. Okay, it continues to move, and now here it has been moving along a specific plane. So now it was moving in a region where there was an orderly arrangement of atoms. Okay, there is an orderly arrangement of atoms over here, and the dislocation was moving in this domain of orderly arrangement. Now when it comes to the disordered region over here, it is no longer able to traverse this or cross this grain boundary. That is because now the slip plane of a neighboring grain is something else. So naturally the dislocation cannot cross over from here to there, and so it gets held up at the grain boundary. When it gets held up at the grain boundary, well, it cannot move further, but then it prevents other dislocations also from joining, because as you see, you have dislocation of this particular sign. Let us say this is a positive sign where the top half plane is present and bottom half plane is absent. Then all positive dislocations which come here will get repelled from this position. So basically when the dislocation gets held up over here, it is unable to move forward. It also does not let more dislocations to come near it. So, but then dislocations are continuously being generated because more force is being applied. The impedance of the interstitials, fellow dislocations is being overcome by application of increasing amount of force. And so this increasing amount of force on a macroscopic scale is called as work hardening. That is because you have generated multiplicity of dislocations by virtue of working on the material, by deforming the material, and this multiplicity of the dislocations further results in an increase in strength of the material. So this increase in strength of the material is macroscopically felt as an increase in hardness of the material. And the reason why the material has hardened is because the dislocations have started moving and they have started multiplying. They have been interacting with each other, they have been interacting with the interstitials, they have been interacting with the grain boundaries, they get held up at the grain boundaries, and therefore they are unable to cross over the grain boundary, impeding the movement of further dislocation. So essentially what happens is that the due to various interactions between a surface defect like grain boundary and a dislocation, point defect like interstitials and a dislocation, the impedance increases, the impedance to the movement increases, therefore the forces required to move the dislocations continue to increase. Now if you apply some heat, for example, if you apply some heat, then what happens is atoms tend to diffuse, atom tends to diffuse, and then the material behaves soft. Why does it behave soft? That is because the dislocations are able now to to move out of any impediment. So for example, let's say this dislocation has got held up at a particular location due to, let's say, an interstitial. Due to so-called dislocation climb at high temperature, where these atoms are able to diffuse out, a dislocation can go to some other plane as a result of that. So vacancies, for example, will help this kind of diffusion of these atoms. So these vacancies, which are point defects, then there are many interstitials which diffuse due to high temperature. So there are again the dynamics of interaction between the dislocations and the interstitial atoms keeps on changing with temperature. Plus the position of the grain boundary also tends to change because of diffusion of atoms from one side of the grain boundary to another side of the grain boundary. So at high temperatures, the resistance to deformation is purely due to different reasons. The mechanism of generation of resistance to deformation is completely different as compared to a room temperature or a low temperature deformation. Now initially, so when I'm saying that the grain has certain dislocations which move under certain pressure or certain load, and this grain boundary is something that restricts the dislocation, it means that the grain boundary is able to withstand the forces which are exerted upon it by the dislocation, because dislocation also has got a stress field, and that stress field would be acting on this grain boundary, but then the grain boundary is strong enough to withstand that stress field. So with temperature, however, the grain boundary becomes weaker and weaker. Why does grain boundary become weaker and weaker? Because diffusion starts, and grain boundary being a region of great disorder permits diffusion through the grain boundary. So grain boundary becomes a channel for mass diffusion, for a large amount of diffusion at high temperatures, and therefore the grain boundary becomes weaker beyond a certain temperature. So initially the grain boundary is strong, and as temperature increases progressively, the grain boundary becomes equal in strength with that of the grain, and then its strength reduces below the strength of the grain. So the temperature at which the two strengths are equal. So, grain boundary is as strong as the grain is called as the equicohesive temperature. So, below the equicohesive temperature, the grain is stronger, the grain the grain is weaker, the grain boundary is stronger. So, grain is weaker means the grain deforms, grain boundary does not deform. So, below equicohesive temperature, the deformation happens purely because of dislocation movement, dislocations in the grain, and that deformation takes place because the grain is weaker, is more deformable. When I say weaker, it means more deformable than the grain boundary. So, grain boundary acts stronger, and therefore, it blocks the movement of the dislocations and results in work hardening. So, the grain boundary is not affected by stress at relatively lower temperatures below the equicohesive temperature. Now, as the temperature rise and reach above equicohesive temperature, the grain boundary becomes weaker because of diffusion, and the diffusion results in the weakness of the grain boundary. So, grain boundary is more easily deformable. So, what happens is the grain is stronger than the grain boundary. So, the dislocations really do not move, because even before the stress needed for dislocation movement has been reached, the deformation in the grain boundary starts, because the grain boundary at high temperatures with all disorderly arrangement of atoms behave like a viscous fluid. So, the grain boundary has characteristics of a viscous fluid, and that deformation in the grain boundary starts at a much lower shear stress as compared to what is needed for dislocation movement. And that is precisely why you use single crystals for turbine blades or equipment which operates at high temperatures. That is because the grain is stronger than the grain boundary. So, you would like to minimize the grain boundary area so that the material is strong. It is able to withstand high temperatures and large loads, right. Now, if you had too much of grain boundary area, if you had lots of grain boundaries here, then what will happen is there are many regions of weakness, namely the grain boundary at high temperature. The load is high, the temperature is high, and therefore, there is a lot of area in the material that is capable of deforming at much lower stress. And so, you will find that the resistance to high temperature deformation will be extremely poor when you need the structural strength of the material for a polycrystalline material, or where the grain size is relatively small or grain boundary area is large. So, the smallest amount of grain boundary area would be can be achieved when you have just a single crystal. So, that is why single crystals are used for high temperature and high load application, as in case of turbine blades. So, that is what is mentioned in this slide over here. I have already discussed the various points which are mentioned here. So, the atomic disorder with grain boundary region will result in discontinuity of slip planes from one grain to another, due to which the dislocation pileup takes place at relatively low temperatures. At high temperatures, the dislocations activity is relatively very small, and the grain boundary activity is large because of the viscous nature of the grain boundary. Now, we come to the equation which relates the grain size to the rate of hardening, because at below equicohesive temperature, where there is a lot of dislocation activity, the source of strength, the source of increase in strength of the material is the dislocation movement, and it is the impediment to dislocation movement. So, if the grain size is small, meaning the grain boundaries are much closer together, then what you are likely to have is impediment to dislocation movement from time to time and again, and therefore, you will get significant increase in the strength for, or rapid increase in strength for a small amount of strain. So, you have to have dislocation moment, you need strain to be imposed on the material, that is a plastic strain, permanent deformation. But then to cause that deformation, you need an increasing amount of stress because of the fact that you have dislocation movement being impeded by various factors, namely the dislocations which are already present, the interstitials which are present, and the pile up at the grain boundaries. So closer are the grain boundaries, greater is the work hardening rate. So that is indicated by what is called as the Hall-Petch equation, where sigma y is the yield strength of the polycrystalline material, sigma naught is a constant, and ky is also a constant, and then you have d raised to minus half, okay, d raised to minus half. So it is inversely proportional to the square root of the grain size or grain diameter as they call it. So if you idealize a grain as a sphere, then it will have a certain diameter, and therefore that diameter affects the strength of the polycrystalline material. So smaller is the grain size, greater is the yield strength of the material. So this is basically a very important equation, and this applies only for temperatures which are below equicohesive temperature, where dislocation activity. So this characterizes the work hardening due to dislocation activity, dislocation movement. Now if you take nanocrystalline materials, and so on, the size effects play a role, and therefore this equation will not apply. This has to be taken with a pinch of salt for nanocrystalline material where grain size becomes extremely small. So this equation is valid for our normal metals which we use. So you may use aluminum, steel, copper, all our engineering materials are amenable for this relationship, but then the grain sizes which we normally use are should be the ones which should be used with this equation. Okay. So now you have the different strains imposed on host atom by substitutional atom, and so the compressive strains imposed on host atom due to large substitutional impurity atom. So it does not have to be impurity, it can be alloying atom, alloying element as well. So you have stresses being imposed by these, and these stresses are the ones which impede the easy dislocation movement, because if you have the compressive field of the dislocation interacting with the compressive stress generated by an interstitial, then there will be repulsion between the two. So it will not aid dislocation movement. On the other hand, if it is the opposite, then it will help dislocation movement, but so the material will tend to behave soft. So it all depends upon how the dislocations interact with the stress fields which are created by the interstitials. So for example, you take a large atom like molybdenum, tungsten, and so on. So they will cause extremely high lattice strains as interstitials, and therefore they will make dislocation movement extremely difficult. So as a result, when you have certain amount of these materials dissolved in steel, for example, then you would, or dissolved meaning behaving as interstitials in steel, for example, then they will generate significant amount of lattice strain due to which the resistance to deformation is increased tremendously, and ductility comes down very rapidly. The material behaves brittle. So brittle means it will not undergo any plastic deformation. It will just crack. It will just like our ceramic plates and saucers crack, right? So that is what happens to a brittle material. So many ceramics are brittle, they fail in a brittle manner. Our tungsten carbide tools, for example, they are of a brittle nature. So they are hard, but they are extremely brittle. So these are the properties of ceramics are like more brittle as compared to metals, and therefore the equation, Hall-Page equation is applicable to metals, so metallic materials, alloys and so on. But then the mechanism with which dislocations are restricted, or dislocations, I mean the movement of dislocations is impeded, is because of these lattice strains and extent of lattice strain, extent of lattice distortion is the one that results in the hardening of the material, or the resistance to deformation of or resistance to movement of the dislocation, which we experience on a macroscopic scale as hardening. There is another mechanism of deformation, and it is other than slip. So, what we were talking about is slip. So, what we were talking about is essentially this dislocation moving along a slip plane, where, so this is the shear plane along which the dislocation moves. So, one crystal slips with respect to another. So, there is in the previous class also I had shown you that the top half of the crystal is slipping with respect to the bottom half. So, that is what we were talking about so far, and the phenomenon is called as slip of one crystal with one part of the crystal with respect to another. Now, here there is another mechanism called as twinning. So, you have what is called as a part of the crystal moving in such a way that it forms a mirror image with about a certain plane. So, now you have initially healthy crystal, and then these atoms, so these atoms have moved. So, these were a part of the orderly arrangement of atoms, but then under certain stress, what has happened is this atom becomes a mirror image of this atom with respect to this plane. So, you take any pair of atoms, they are, so this atom and that atom are a mirror image about this plane. Similarly, this atom and that atom are mirror image about this plane. So, this plane is called as the twin plane or the twin boundary, and it shows itself in this form in a microstructure. So, if you look at the polycrystalline material like brass, for example, here twinning takes place. So, while rolling, you will see that the material develops these twins. Similarly, stainless steel, austenitic stainless steel also develops twins. So, these are called as mechanical twins, because these have been formed as a result of applied mechanical working. But then there are other reasons also twins can form. So, that is why the twins are not purely because of mechanical working, but even while annealing, while giving thermal treatment. Okay. So, while heating the material, while conducting a heat treatment, twins can form, and these are called as annealing twins. So, basically twinning occurs on a definite crystallographic plane and in a specific direction, and all this depends upon the crystal structure which we have already studied. Now, at room temperature conditions, the twins are formed even at high strain rate. So, if you are trying to deform the material at a very high strain rate, then instead of slip, you have what is called as twinning taking place. So, twinning takes place when slip is not possible. Normally, deformation takes place by slip, but wherever slip is not possible, as for example, at high strain rates, you have twinning taking place. But then even in copper, even at normal slow strain rates also twinning takes place. It is not that you always need high strain rates, but there are different causes for twinning. So, what I am saying is that you have shear forces being applied during mechanical working, due to which twinning takes place, during annealing twinning takes place, and at high strain rate, at high speed of deformation also twinning takes place. That is the point I am trying to make. So, the process of twinning is something like this. So, you have a polished surface like this, and this is the arrangement of atoms, and there is a shear stress which is acting. Now what happens is now this remains as it is, and then so these are the positions of, so closed circles are the positions of atoms which change the position, whereas open circles show that the position did not change. So you have these atoms which have moved. So this is a new position of the atom, and so these are the 4 atoms which have changed position, 1, 2, 3 and 4. Yeah. So these have changed position to this, and so you have a new position where the so this is one twin plane, this is another one, because this and this are symmetric with respect, or mirror image with respect to this this plane, right. So this is a twin plane, and so is this. So here is the twin plane. So you have this crystal twinning in about 2 twin planes. There is another defect which can come into play, and again you cannot eliminate it completely, and that is called as stacking fault. Now we know that there is a certain stacking sequence to generate different kinds of crystals. So you have a stacking sequence of AB, AB, AB for HCP, hexagonal closed packed crystal. So where the top hexagonal and the intermediate plane which has got 3 atoms here. So A, B, A, B is the order of stacking with one on top of the other. But then sometimes one of the planes can be missing, and so that is called as a stacking fault. So there is some irregularity in the stacking sequence that comes into play, and this irregularity is called as a stacking fault. So you have in case of a face centered cubic structure, the sequence ABC, ABC. So you see that the atoms which are of similar color form one single plane. So you have ABC, ABC as 3 planes being stacked together. So this stacking sequence gets disturbed at times, and that is what generates a stacking fault. And now this stacking fault doesn't directly interfere with the work hardening as such, but what happens is that depending upon the energy that is required to generate a stacking fault, depending on the energy that is needed to create a stacking fault, the possibility of material undergoing either so-called dynamic recovery or dynamic recrystallization. So some of these transformations get affected by the energy that is required for generating a stacking fault. So these are events taking place at relatively high values of strain. So we will see them a little later when we look at the mechanical properties, but just remember that these stacking sequences get disturbed, and these will affect the method in which the material will tend to soften beyond a certain limit of hardening. So I have been telling you that dislocation moment gets impeded, and therefore you need to apply increasing amount of load. The stress continues to increase, and that we call as work hardening. But the question is, can the work hardening go on forever? The answer to it is no, because as you continuously have work hardening taking place, then there are, so as the energy, the so-called stored energy in the form of dislocations, stored energy of so-called cold work continues to increase, then these defects accumulate there, and then they undergo either so-called dynamic recovery, which means that there are subgrain boundaries formed as a result of excessively high amount of dislocations getting piled up, or the material recrystallizes, meaning the stored energy of cold work is dissipated in generating new crystals. Now, what will happen in which material is governed by the so-called stacking fault energy, meaning energy that is needed to generate a stacking fault. So, now we will continue with the explanations a little later, but then it is enough for now to remember that the stacking sequences can get disrupted and it can affect the deformation in the later part when the material has work hardened a lot and material starts getting softened or starts behaving softer as a result of either dynamic recovery taking place or new grains being formed by recrystallization as a result of these stacking fault or stacking fault energy, as we call it. So, now let us come to the details about the stacking fault. So, these occur during the crystal growth and as a part of other defects, and they evolve from other defects, because these are other defect means dislocation. So, if the dislocation pileup becomes excessive, the dislocation density increases too much, then you can generate a stacking fault, because these are defects. If the defects get accumulated to a great extent, it gives rise to another defect, namely the stacking fault. So, that is what is being said here, they evolve from other defects. So, let us see what is a stacking fault, and you have A plane, B plane and C planes being, so ABC is the sequence, and that gets disrupted. So, you have a perfect crystal, but then you have a stacking fault being developed. So, here CBA is the regular arrangement of atoms, and now here that gets disrupted and you have ACB, ABA, CBA. So, here that C layer is missing, due to which a stacking fault has been generated. So, what happens is that when a stacking fault is created, you have what is called as partial dislocations getting formed, meaning you have one dislocation splitting into two. So, basically you have two partials, so which get formed, and then you have frank partial dislocations as shown over here in a crystal. So, you have if you look at the interconnections between these atoms of different colors, it will be clear to you how these stacking fault results in the or how say vacancies, agglomeration of vacancies result in a stacking fault. Similarly, if you look at so when these vacancies collapse, when there are too many vacancies generated, they collapse, and then there are interconnections which are made resulting in a stacking fault. So, here you have there is a stacking fault generated due to too many vacancies being present here. So, similarly you will have stacking fault generated because of too many dislocation being present, because absence of half plane is effectively having the number of vacancies which would be present in that particular half plane. So, to summarize, what we see is that mechanical properties, namely the strength of the material, the structural strength, that is what we are worried about all the time, are the outcome of interaction among defects together with crystal structure and interatomic forces of attraction. Now, you have interatomic forces of attraction which are the same depending on the atomic diameter, radii, and the configuration of electronic configuration of atom. So, that remains a relatively constant factor. The strength of the metallic bond being non-directional again becomes a constant factor. The crystal structure, that is an orderly arrangement of atoms, whether it is FCC, BCC or HCP, remains constant for a given temperature. The crystal structure, mind you, changes with temperature. So, it is not that the crystal structure always remains constant, but yes, the crystal structure for a given temperature will remain unchanged. Now, the issue is, how does the mechanical property change in spite of the interatomic forces being the same and the crystal structure being same? That is because of the interaction of dislocations and the strengthening effects of the different kinds of interactions. So, mechanism of generating strength in metals as opposed to polymers is therefore very different. So, we have been considering metals, we have been considering orderly atoms or orderly arrangement of atoms. In metals and ceramics, you have a difference of metallic bond versus ionic bond. Well, in case of ceramics, since these are compounds, these are compounds like silicon carbide, tungsten carbide and so on, these therefore are not deformable. So, unlike metals where you have dislocation movement, management of defects, interstitials, impeding motion, etc. Since there are no dislocations to move, these are compounds, the bonds either are made or undone, meaning broken. So, there are only two states, either integral or broken. So, these materials therefore behave in a brittle manner, whereas the deformation is characteristic of metals because you have the dislocations, they are able to move, then you have the grain boundaries impeding motion of dislocations, interstitials and so on. So, the mechanism of generation of strength in metals has a wider scope. You can generate materials of different strengths by controlling the extent of defect density, their interactions, whereas in case of ceramics, the chemical composition is the one, the chemical compound that forms is the only one that governs the strength. There is nothing else with which you can control the strength of a ceramic material, and it therefore behaves in a brittle manner. So, we will see in subsequent classes how metals and ceramics are different from polymers, because polymers have a different way of generating strength. So, how do polymers generate structural strength is something that we will see in the next class. But since we have been discussing metals for such a long time, we can solve a few problems. So, we have problem set 1 where the first problem is about silicon having 3 naturally occurring isotopes and with different atomic weights as shown over here. So, on the basis of this data, confirm that the average atomic weight of silicon is so much. So, we need to check whether the silicon has got whether you get this as the average atomic weight. So, the average atomic weight is essentially a linear combination of the percentage of a particular isotope available and its atomic weight, and therefore, we have 0.9223 into 27.9769, which is the atomic weight of silicon 28. Similarly, you have 0.0309, which is 3.09% of 30 Si. So, it has got an atomic weight of 29.9738, and so we add them these 3 together. The third one has an atomic weight of the second one has of 29 has got atomic weight of 28.9765, and it is present to the extent of 4.68%. So, 0.0468 into 28.9765 is therefore, this gives you a total of this. So, basically the average atomic weight of silicon gets verified. We have done this type of problem when we were in one of the classes, one of the lectures. We had done numerical, during which we have done this derivation of differentiating this energy curve. So, basically this is the interpotential curve between 2 atoms, and so it tells you the equilibrium separation between the two atoms where the energy is minimum. So the interatomic separation will be governed by the position of minimum energy at which the other atom will be located with respect to the first one. So you have the energy of attraction and repulsion giving the total energy, and when we differentiate this energy with respect to the separation distance and equate it to 0, then we get the minimum on energy, and that radius of separation is the interatomic separation between two atoms, or equilibrium interatomic separation between two atoms. And it also, and the differential of this with respect to R turns out to be the force, the interatomic force acting on the atom. So what it means is that when the force acting becomes 0, the atom is stable, is located at a stable location with respect to another atom. So that is also a meaning of differentiating this with respect to R and equating it to 0. So this gives you a point of minimum energy, so the separation between two atoms having minimum energy as well as a 0 force. So one has been asked to find out the equilibrium atomic spacing or ionic spacing. The principle remains the same. We have done it for metals, but then here we are talking about ions. So equilibrium ionic spacing has to be found out. So the principles remain the same. The issue is that the application of these values will be different, of course, and the application remains very similar to those of metallic materials. So this ionic spacing is equilibrium ionic spacing would therefore be calculated by equating it to 0 and arriving at minimum energy and 0 force. Okay. So we have a follow-up problem here. Calculate the force of attraction between a Ca2 plus and O2 minus ion, the centers of which are separated by a distance of 0.125 separated by a distance of 1.25 nanometers. Now these are two ions Ca2 plus and O2 minus. The centers are separated by a distance of 1.25 nanometers, and if you look at the ionic radii of calcium, for example, the ionic radius is 0.1 nanometer. Ionic radius is 0.1 nanometer, and that of oxygen, okay, that of oxygen is O2 minus O is 0.14, right. So it has got 0.14 and ionic radius of oxygen and 0.1 as the. So now the two radii are 0.1 and 0.14. So if they are touching each other, then the separation will be, center to center separation will be 0.24 nanometers, but that is not the case. The separation here is 1.25 nanometers. So we need to find out the force of attraction between Ca2 plus and O2 minus ion centers which are separated by this distance, and the same equation which we used in case of atoms applies. So the source of attractive force, force of attraction is different between atoms in metals as compared to ions in ceramics. So there is data which is given here. So one can use, for example, aluminum oxide. You would use the same set of data. You have an ionic radius of 0.053 and oxygen has got 0.14. So the center to center separation, if the two ions were touching each other, would be roughly 0.19 nanometers. So basically one can calculate the minimum center to center separation between these two ions for one positive ion and another negative ion. So, these elements have been arranged in alphabetical order. So, you have starting with A up to Z over here, zirconium, and so this data can be used for solving subsequent problems as well. Similarly, there are data on atomic radii and atomic structure. So, this is another useful table which tells you under normal conditions, room temperature conditions, what is the structure of aluminum, cadmium. So, these are all room temperature structures. The problem here is about indices for the directions shown in the cubic unit cell. So, we have seen how we calculate we find out the Miller indices for directions and Miller indices for planes. So, you have these 4 directions A, B, C and D. So, what you do is you subtract the x component from the head to you subtract the component of tail from the head. So, x head minus x tail will give you the x coordinate of the direction x. So, y head minus y tail will give you the index of the y index of the direction. So, this way I have put together a table. X2, Y2, Z2 refers to the head and X1, Y1, Z1 refers to the tail. So, head has got coordinates for A it is 1, 1.33. So, the head for A has got 1 and Z is 0.33, 1/3, right, and so that is been put here. Its tail is at 0.66. So, it is 0.66. So, if you take the direction A, it has x1, y1, z1 of this. So, now you subtract the x coordinate of the tail from that of the head. So, x2 minus x1 gives you 1, 1 and minus 0.3, and so what you do is that you convert this into an integer, and so this becomes 3, 3 and bar 1, because now when you multiply this by, actually this is 0.33. So, because Z2 minus Z1 is essentially 0.33, right, Z2 0.33 minus 0.66 is minus 0.33. So, that is why if you multiply everything by 3, then you get integer values. So, you have 3, 3 bar 1 as the Miller indices for this particular direction A. Similarly, for B, C and D, one can calculate, try it yourself, follow the same methodology, and I am sure you will be able to get it. Now, coming to the Miller indices for planes, we have Miller indices corresponding to the intercepts with various axes. So, for example, plane B has got an intercept of half and 1/3. So, with x and y, it has got an intercept of half and 1/3, but it is parallel to the z axis. So, it has no intercept at all with z axis. So, intercept at z axis will be infinity. So, now you reverse these meaning take reciprocals of these. So, you have 2, 3 and 0. So, this plane therefore will be 2, 3 and 2, 3, 0 plane, because the intercept on the z axis is infinity, reciprocal of that would be 0. So, reciprocal of this is 2, reciprocal of this is 3, and z reciprocal is 0. Plane A has got intercept 1, 1 and 1. So, this has all 3 intercepts are 1, and therefore, the reciprocal is always 1. So, it is a 1, 1, 1 plane. So, plane A is a 1, 1, 1 plane, whereas the plane B is 2, 3, 0 plane. So, this is the way you determine the Miller indices. Now, you use the lecture notes for finding the Miller indices for a hexagonal HCP structure, hexagonal close pack structure or hexagonal unit cell. So, for this plane you have A1, it is parallel to A1, A3 you have an intercept of 1, okay, and it is again parallel to the z axis, right, it is parallel to the z axis. Intercept in the direction of A2 is, well, that can be calculated from the geometry, that will also turn out to be 1. So you have these 4 intercepts, and based on this you can again get the Miller indices for these planes. Now given the Miller indices, you have to sketch the planes. Now so far what we have been doing is, we had been considering the Miller indices. I mean, we have been deriving Miller indices from the planes which had been sketched. So now we need to sketch 1 0 bar 1. So we have the reverse procedure. So if you take a cubic unit cell, then the intercepts will be 1 0 again -1 when you take the reciprocals. For plane B, it will be half -1 1. These are the intercepts made by the plane with the 3 axes. For plane C, it is going to be parallel to the x axis, because x will have an intercept of infinity. So naturally the plane will be parallel to the x axis, and then it will have intercept of 1 with the y axis and half with the z axis. So you can sketch these accordingly. Similarly for plane D, it is 1/3, -1 and 1/3. So you can sketch a cube, identify an origin, and then plot these points at the appropriate coordinates with respect to that origin, and then you join the 3 points together to get the plane. So F is of course very simple. You have reciprocal of 1 is always 1, and therefore you have -1 1 -1 as the intercepts. For F it is -half 1 -half 1 half. Okay, for F it is -half 1 and half. For G it is 1/3 -1 and half. 1/3 -1 and half for G, and for H it is 1/3. Now it is infinity, meaning it is parallel to the y axis. So this plane H will have to be parallel with the y axis and have an intercept of 1 with the z axis. So 1/3 as the intercept with the x axis, parallel to the y axis, and intercept of 1 with the z axis. So basically these are some guidelines for solving these problems. Try to use the lecture notes for solving these. The slide which we have already shown you earlier, use the previous lectures, and in case there is a difficulty, let us know. So with this I would conclude this lecture, and so this is the last problem which we have solved. So if you have any questions, let us know. Thank you.